Okay, so it's time to start. So we are still in the topic of game theory. So last time we talked about some games, right? We give the setup, we introduce the notion of Nash equilibrium, and then we studied some of the games and we figure out the Nash equilibrium, and we also have examples of a Nash equilibrium may not be the so-called optimal solution. Okay, so so today there are two topics. One is we have to finish the typical ones. So we are going to introduce probability so that some problems which do not have Nash equilibrium in the so-called pure strategy situation now have a Nash equilibrium. Okay, so we are going to do that, and then I will probably say more or less the same thing, but use a slightly more abstract setting. So it's like talking about mathematical theorems and so on and so forth. So I believe the part here, you can treat it as a revision or as looking at the same thing one more time, right? So, but in a slightly different setting. So there are a little bit mathematics involved, but hopefully not too much. I put it optional means because this is a general education module. So certain things you don't need to know the proof and so on and so forth. Okay. All right. So let's carry on from where we finished. So we have seen these slides before. So we stop on Tuesday after we talk about this example. So this example is an example of a zero-sum game. And the example says there are two companies selling mineral water, and the policies are they have a choice of setting the price at $1 or $2. Okay, so we have seen this kind of matrix many times. So this is called the payoff matrix. So we have two companies, company X and company Y. So company X has two possible moves, or people call it strategies, okay. And company Y also have two possible moves. So there are two strategies. Now, for each pair of moves, right, we call it a strategy profile. So if X play one of the strategies and Y play one of his strategies, so you will get X will get some reward or get some negative reward, punishment, right? So we record a situation in a matrix. So in this matrix, I only record the reward of X because this is the zero-sum. This is an example of zero-sum matrix. If you know the reward for X or the payoff for X, then you know the payoff for Y, which is the negation of the payoff of X, right? Because the total sum has to be zero, okay? So in this situation, we have, suppose both company X and company Y selling the bottle of water at the same price, then it's 0-0. So there's no gain, no lose. But if one company sell at a lower price, then somehow he gets a big payoff, right? For example, in this entry 5,000, if the company X selling the water at $1 and company Y selling at $2, and then X has an advantage, so he will get positive $5,000. And Y will lose that amount, right? Because it's total. The total is 0. Okay, so this is the setting, right? So now, so we introduce the concept of saddle points, right? So in this matrix, the saddle point, in this simplified matrix, the saddle point is defined to be the minimum of some column, at the same time is maximum of, minimum of some row, but maximum at some column, right? For example, this entry 0 here, he is the minimum of 0 and 5,000, right? So among these, if you compare these two, he is less, right? So this is a minimum of row 1. At the same time, he is maximum of column 1. So therefore, by our definition, we call it a saddle point, okay? So for example, this 1, 1 is a saddle point, okay? Now, here's a claim. At saddle point, or sometimes it has more, saddle point, no player wants to change. So therefore, it is a Nash equilibrium. Okay, so last time probably I didn't explain clearly, but let me repeat it. And then in the second half, I will repeat it again. Okay, so why at saddle points nobody want to change? So I want to say it one more time. Okay, for example, we are looking at this saddle point, right? So repeat one more time. He is the minimum of this row, and he is the maximum of this column, okay? So I want to convince you there's no incentive for X to change. Why? Because here, X can only move between he can only change the rows, right? So he'll fix this column, right? But this guy is the maximum of this column. So therefore, if he moves away from maximum, so he will lose some money, right? And we believe players are rational, whatever. So they don't want, X has no incentive to move, because if he moves, in this particular example, he will lose $5,000. So he does not want to move, okay? Now, how about Y? So is there an incentive for Y to move? Okay, so Y can switch columns, right? So Y's strategies are either this column or that column, okay? So is there any incentive for Y to move from 0 to here? Well, here, although on the matrix, this number is bigger, but remember that this is a simplified payoff matrix. So the actual payoff for Y is the negative of this value. So therefore, the larger the number here, the worse for Y it is. So therefore, Y, actually for Y, the value here should be negative 5,000. So therefore, Y does not have incentive to move, right? So this is why at saddle points nobody wants to move. And we have defined the so-called Nash equilibrium exactly this kind of situation. It may not be the optimal, but nobody wants to move. If you move, you get worse. So the Nash equilibrium is some special point where nobody wants to move away from it. Okay, so if you believe the first sentence, then by definition this is a Nash equilibrium. Okay, so this is the example we have seen. Okay, so now we have seen several easy situations, right? We have seen zero-sum game with saddle points. We have seen a variable sum game, but somehow with dominant strategy. We have seen, for example, the arm race or the prisoner's dilemma. There's a dominant strategy. So we have seen those things. So if we are lucky, we have seen dominant strategy, or if we have seen saddle points, then the problem is solved. It's easy to solve. But in real life, it may not be, we may be unlucky, right? So let's consider the following zero-sum game with this payoff. This is just an artificial example, right? So here there's no saddle points. So first, this is again a two-player game, and each player have two strategies or moves like this. And this matrix shows the payoff for player one. It is zero-sum, so the payoff for player two is a negative of the value showed up here. Okay? Okay, so now here, let's see, there's no saddle points. For example, look at the first row. The minimal element is here, is -1. But he is not the maximum because 1 is bigger, right? The same for the second row. So there's no saddle points in this matrix. Okay, so now let's see what would happen, right? Okay, so let's assume player one choose a strategy. For example, he choose move 1, right? He believed that this is his best move. So he will consistently play strategy 1, move 1 here. Okay, now player 2, he's clever, right? So she is clever. Okay, she noticed this. So she will play move 2 consistently, because when she play move 2, player 1 gets -1. So player 2 wins 1, right? So she wins 1 every time. So therefore, if player 1 always play strategy 1, then player 2 will notice this and play strategy 2. So therefore, player 2 will have an advantage. Okay? Now, however, so here there. Okay. However, if player 2 stick with strategy 2 here, right? Then player 1 will notice this, because player 1 will notice she always play this, and player 1 will change to strategy 2 here, because if she move down to the second row, she will get she wins 1 every time. Okay, so we are here and here. Okay, and then, however, if player 1 always play strategy 2, player 2, again, she is clever, so she will not play move 2 anymore. She will move to here to play strategy 1. Right? In this case, player 2 will win 1 every time. Okay, so we are here and there. Okay. Well, however, if player 2 always play move 1, player 1 is smart, so she will now go back to row 1, right? So she'll win 2 every time. Now this is a cycle. So everybody will change and change and change and change, and so there's no best strategy, and no matter what you do, you are not in the optimal position. There's advantage to move away. Okay. Okay, so the new idea is, well, you should not stick with one strategy. So you have to surprise your opponent. You have to mix the strategy together. So the new idea comes in is each player should choose at each play of the game a strategy at random. So that's why we bring in probability. Okay, so now we are moving from pure strategy, which are the ones does not involve probability, to so-called mixed strategy. Right? So by choosing a strategy at random, say we choose strategy with certain probability, the other player cannot guess what we are doing, right? So the game is different. Okay. So now the problem for each player will change to this problem. So we have to set the probability so that we get optimal results. Right? So the problem change into some calculation of probability. Okay. So this will, by introducing the mixed strategy, it will solve the zero-sum games without saddle points and variable sum game without dominance. So on Tuesday, we know how to solve zero-sum game with saddle points. We know how to solve things with dominance. Now, today we learn some tricks to solve things without these. We are not so lucky for this. Okay, so the first half will be devoted to this artificial example. So we are going to look at a game of tennis. Okay, so we have player 1, receiver, player 2, server, whatever. So there are two options. So receiver will predict, right, something like whether it's forehand or backhand, and server will do the same. Will serve use forehand or backhand. So to the forehand or backhand to the receiver. Okay. So now the payoff was set up in this way. So if the server serve to the forehand of receiver and the receiver predict he will serve, and then the receiver has an advantage. So he will get payoff 4, and the server will have payoff 1. Now suppose the server served to the backhand side of the receiver, but the receiver ill-prepared, right? She thought this is the forehand. And then the server will have advantage. So the server will get 4 and the receiver get 1. Anyway, so something like this, right? So the same for the second row, okay? Okay, so now here, this game, like the zero-sum game we showed, that there's no obvious best strategy. So if you stick with one strategy, the payoff can change. So for example, if the receiver stick with the forehand, always predict forehand, when the server notices it, it will serve to his backhand. Right? So there's no obvious best strategy. So as we said before, we should mix up the strategies randomly so that we surprise the opponent. Okay, so here is the official description of mixed strategies. So in other words, one adopts a probabilities approach by using strategy J with some probability Pj, where the sum of the total probability is 1. Well, in our course, I think the R is at most 3. So in the lecture, I'll talk about two possible strategies. In the tutorial, there is one. We mix 3 strategies. Okay, so the general setting is you can have finitely many strategies, and each one of them you can assign a probability. Okay. So this is called mixed strategy. Mix means you mix them, right? So you don't always stick with one. You sometimes play this, sometimes play that, and so on. Okay, so in the example of tennis, which has no Nash equilibrium in the pure strategy, so let's bring in probability, right? So let's say the receiver predict forehand with probability P, and the server serve forehand with probability Q, right? So we assign probability. So therefore, we actually expand the set of possible strategies. So each player has a set of strategies given by a probability, right? Suppose in a pure strategy, we only have 2 strategies, S1, S2. Now, here, when you change P, you have a family of mixtures of S1, S2, right? So now each player has a set of strategies given by P in the interval 0, 1, because it's probability, so it's interval 0, 1. So therefore, not only we have two strategies, we have a mixture of them. So the set of strategy profile for the game is now a point in the unit interval, because P will change from 0, P can change from 0 to 1, Q can also change from 0 to 1. So rather than just the matrix, okay. So the question is, how does one decide the best or some kind of equilibrium, right? Okay, so the answer is we have to calculate the expected payoff on each mixed strategy profile, and choose the one that maximizes the worst expected payoff, right? We have seen this. Now the only thing new is we add the word expected on everywhere. Okay, so now to study mixed strategy, we have this probability floating around, right? For example, for receiver, for player 1, she will use with probability P, she will use the strategy 1. And with probability 1 minus P, she used the second, right? For server, for the player 2, she will use with probability Q strategy 1, and 1 minus Q for strategy 2. Okay. Now we have to calculate the so-called expected payoff. Okay, so now let's first consider from receiver point of view. Okay, so we are here. Let's consider the receiver. So from receiver point of view, I'll go back to the table in a second. Right? So I'll finish this item and go back to the table. So if the server plays F, use her first strategy, and then the expected payoff is 4P plus 2 times 1 minus P. And okay, so let's go back to here. So now we are receiver, right? Suppose our opponent play strategy 1. What is the expected payoff? Okay, so with probability P, I will get payoff 4, right? So with probability 1 minus P, I is receiver. I'm now receiver. Okay, the probability 2. The payoff 2, right? So the expected payoff will be the sum of these. Is a weighted sum of these, right? So it is P times 4 plus 1 minus P times 2, right? So, okay, 4 times P plus 2 times 1 minus P, right? So you get 2P plus 2, okay? Now, this fact is useful in a moment, and also probably in the second half when we look at mathematics, this fact is useful. So the expected payoff increases with P. When P gets bigger, because the coefficient is positive, so the payoff is bigger. Okay. Now this is for the first case. The server plays her first strategy. Now suppose the server plays the second strategy. It's the same. So symmetrically, you get expected payoff is this. Okay, so let's go back to the matrix. Now, suppose the server play this strategy. Now, we are receiver, so with probability P, we get 1. So it's 1 times P, plus with probability 1 minus P, we get 3. So it's 1 times P plus 3 times 1 minus P. Okay, so let's see whether Okay, 1 times p plus 3 times 1 minus p. So you get 3 minus 2p. Okay. Now this will be a decreasing function with respect to p, because when you increase p, the leading coefficient here is negative, so you get less, right? So this is just some observation. Now, what is the right balance, right? So you have two expected payoff, and how do we balance? Okay, so here, so the two expected payoffs can be, okay, we draw a picture like this. So, okay, so let me explain the picture. So this, from 0 to 1, indicates the probability, because for the receiver, he has a probability p choose his strategy 1, right? So p can vary from 0 to 1, okay? And then the expected payoff. So when the server serves 4 hands, somehow you get the payoff is 2 plus 2p, right? Let's see. Right. So if the server plays f, then the expected payoff is 2p plus 2 plus 2p. So it's here, right? So suppose the server serves 4 hands, the payoff is like this. Okay. Now, if the server serves backhand, then the payoff goes from is this line, is 3 minus 2p. Okay, so if the server plays backhand, then the expected payoff is 3 minus 2p, right? So if I plot the picture, is when p equal 0 is 3, when p equal 1 is 1, so it goes down, right? Now, the picture will show that these two things intersect at some point. Okay, we'll see that this is not a coincidence. So, in the second half, we'll see that if the game has no saddle points or no dominant role, the picture must be like this. Okay, in any case, in this particular example, we know the line will cross at here. Okay, so this point, if you calculate, so this is the equation to find the intersection. So you find that when p equal 1/4, you get payoff 2.5. Okay. Okay, so at this point, the expected payoff is 2.5, regardless whether our opponent serve forehand or backhand, right? Because it hits the same point. Okay. So the picture is all right, right? You understand? Okay. So now, if the receiver, so now I'm trying to say that this point, when p equal 0.25 or when p equal 1/4, this point is special. Okay. So if the receiver use a mixed strategy with p less than this point, okay. So suppose I'm here. Suppose the receiver use some strategy with probability p less than the critical one, the 0.25 here, and then the other guy can make the payoff less, right? If the other guy keeps serving with forehand, and then you are going to, the minimum of the two is here, right? So you get less, the player 1 will get less, right? Now, if player 1 choose a probability somewhere here, for example, he choose, that's extreme case, we'll always play this. And then, again, player 2 will notice this, and player 2 will serve backhand, so that the payoff for player 1 is worse, right? So we are here. If the receiver use probability less than the important one or the critical one, then the server can take advantage. If the receiver use P bigger than that, again, the server can take advantage. So therefore, at this point, the receiver payoff is the same. It's always the same. So, and actually is the sort of the best, right? Is that you see the worst payoff will be this line segment, right? So therefore, here is the best possible worst payoff. Okay. Okay. So we are here. So you'll get receiver is the same regardless what server does. Okay. So this point is important. So in the previous analysis, we have identified an important concept, the notion of indifference. So if the receiver play with that probability, he doesn't care what server does, right? Okay, so receiver has found a strategy, that is this one, which guarantee maybe her or payoff at 2.5, regardless what the opponent does, right? So we say that the receiver is indifferent to server's actions, right? So I'm just repeating myself. Now, if the receiver deviate from this strategy, then server can exploit this misstep, which then result in a lower payoff for the receiver. So it's not balanced. Okay. Okay. Now we can look at the same thing from the server point of view. Okay. Now things are more or less symmetric. So I'll go through this rather quickly. Okay. So now, I should have changed this. So it should be the other way. Okay. So from server point of view, so the server can choose her probability Q. Okay. So server can choose the strategy 1, forehand strategy with probability Q, and then 1 minus Q for the backhand. Okay. So let's calculate the expected return, payoff for server. Okay. So then the analysis for the server will be what happens if the receiver use forehand, predict forehands, right? So if the receiver predict forehands, then server's expected payoff will be Q, which is this 1 times Q, plus 4 times 1 minus Q, right? So it's 1. So it's this number. Okay. Now, if the receiver plays backhand, and similarly, the server's expected payoff will be, so here's his payoff times a probability, 3Q, plus 2 times 1 minus Q. 3Q plus 2 times 1 minus Q. So this is 2 plus Q. Okay. Now, the same thing happens, right? Okay, so you can plot these two lines, and guaranteed they will intersect at some point. Then we equate the equation, we find the point of intersection, and then the expected payoff, the same story happens. So just like what we have done before. So this point is special. This point is Q equals 0.5. Right? Okay, so now let's wrap up the discussion. So we have found some special points for player 1 and some special point for player 2. Okay. So we have found a solution profile, P and Q. For P is 0.25, for Q is 0.5, right? So where each player is indifferent to what the other player does, right? So and which the game is fair, is everybody have the same, the expected payoff is 2.5. Okay. Now, I want to say this is the equilibrium. Okay, so nobody wants to move away. Actually, we have seen it, right? So is there any incentive for either player to deviate from this strategy profile? Well, no. So if you move away, then the other guy could take advantage. So nobody wants to move away. And okay, anyway, so this is probably less important. Okay, so the conclusion is the strategy profile P with a pair P and Q equal to the special spot we found is a Nash equilibrium in a mixed strategy. Okay, so this is the solution of that particular game. Okay, try again. Let's recap this, right? So the tennis game, obviously, is a game. So this game, no obvious solution. Therefore, no dominant, no saddle points. So we introduce probability, and then we talk about mixed strategies. So we calculate the equation. So we calculate the expected payoff, right? And then we plot the line where we solve this equation, and then we find some special points. Okay, so the special point turns out to be the Nash equilibrium. So that's the steps we solve the problem. Is it clear? So bring in probability, calculate the expected payoff for each case, and then have a system of equations, and then you solve the equation, find the special point. Okay, so that's the overall algorithm. Okay, questions? Yes. Yeah, okay, good question. So here, this pair, unlike the pure strategy, right? Pure strategy will say the forehands or backhands, right? Pure strategy is there's only two choices. So if we choose, if we stay with pure strategy, the equilibrium will be a strategy profile. So it's either FF or FB or BF or BB, right? So suppose let's choose BB. It means receiver always predict the backhand, the server always serve backhand, right? So that's the pure strategy. So the meaning is very, very clear, right? So now her question is, now instead of telling me what strategy you use, you give me this pair of numbers, P and Q. What does this mean? Right? I believe that's the question. So what does this mean? So this means the player one should mix the prediction of forehand, backhand with this probability. So it doesn't tell you on each particular game what he or she has to do. But if, so you see all these expectation, so it's like you play the game over and over again, right? So the two guys always play this, and then in the long run, what do you get? So this P and Q is very vague. So it just says player one should mix the prediction like this. So in other words, maybe 1 out of 4 times she will prepare the forehand, and 3 out of 4 times she'll prepare the backhands, right? Something like this. So it's not a very, very clear instruction. It doesn't tell you on this particular game what you do. But suppose you play lots of games, and then you should try to use this probability to predict forehand, right? So this is the mean. Does it help? Okay. Yeah. So probability is weird, right? So it tells, for example, if I say this event happened with probability 0, it doesn't mean it cannot happen. It may still happen, but it's just very, very rare. So it doesn't tell you an exact thing, but somehow in the long run, in long term, and then the pattern will show up. So this is very weird. But for people who are familiar with statistics, this is quite natural, right? So it doesn't tell you what will happen, but they'll tell you if these things happen over and over again, then this is a pattern. Okay. Can we move on? Yes. No. In this case, because the sum of the... So the question was, is this a coincidence that both of them always get 2.5? So the answer is, this is a coincidence. Let's see. This is because the 4 plus 1 is 5, 2 plus 3 is also 5. So everywhere the sum is 5. So if this is a constant sum game, and then somehow, so you will see, probably you will see the example in tutorial where it's not the same. Any other questions?
So the assumption is that because the computation is always from the other person's perspective, so because it's a constant sum game, so if the other player is worse off, that means you're better off. So
Yes.
That's why it only works for constant sum game. If it's a variable sum game, I might also be worse off if I choose another strategy.
Could be, yeah. That's a comment, right? Okay. Okay. So what happens if we have 3 players, right? So in the tutorial problem, we have 3 players. So in the 3 players, so let's say we have 3 strategies here, 3 strategies there. Not okay. 3 player will be more troublesome. Okay, so take game theory, then you'll see 3 players. Well, okay, so that in the tutorial problem, you'll see 3 strategies. Okay, so other than the 3 players, anything else? Okay, so that no. Yes. So probably I'll delay the answer. So after the break, we'll look at some theory. So in the theory, probably you will see the answer. Okay, so let me just okay, so this finished the tennis game. So the next, there's a very short example about this coin. So we have seen this example, matching pennies, right? So player 1, player 2, just the 2 person, each one of them prepare a coin, and then if it's head and head, player 1 wins and player 2 lose, right? So we have these. We have seen that this zero-sum game has no saddle points. So how to solve them? So we use the mixed strategies. So we bring in probability. So player 1 will play head with probability P, right? And then play tail with probability 1 minus P. Player 2 will do the same, Q and 1 minus Q. Okay. Now, from player 1's point of view, okay, so now we calculate the expected number. So the expected payoff is, okay, so if player 2 play head, the expected payoff is 1 times P plus minus 1 times 1 minus P. So it's 2P minus 1. Now if the guy play tail, so it's minus 1 times P plus 1 times 1 minus P. Right? Minus 1 times P plus 1 times 1 minus P, so it's 1 minus 2P. So now equate this, we get P is half. Well, this is not surprising, right? So you don't consistently play always play head, then the other guy will win, right? So it's half and half. Now the same logic applied to player 2. So your shield also choose Q equal 0.5. So this half-half is the Nash equilibrium for this game. Okay? All right, so then I think that's, okay, so let's take a break. So after break, we'll see more or less the same thing, but in a slightly more abstract setting. Right? You won't see numbers. You'll see A, B, C, D. And so it's more or less the same thing. Okay, so let's take a break. Okay, so I guess we can start, and maybe we'll finish slightly earlier, but okay. So the second half will be some theory. So I want to look at a very, very special case. So the special case is they call it small game, right? So it's probably the minimum the game. So the game will have two person, and it's zero sum, and each player has two strategies. So it's just the matrix we have seen over and over again, right? So the three-person game he asked would be beyond this, or you have lots of moves, and so also beyond this. So we look at this very, very special case. Okay, so we'll prove that the Nash equilibrium always exists. Okay, so we have a game, right? And if you remember in the previous lecture, we say Nash in 1950 showed that if you have finite many players, each player has finite many strategies, then the equilibrium always exists in mixed strategies, right? So now we have this special case. So we have two players and each player have two strategies, and also we assume it's zero sum. So we have very, very special case. Now I want to convince you that in this special case, we can always find Nash equilibrium, no matter what payoff it is assigned. Okay, so now the discussion will be in two cases, just like it's a good revision, right? So we did it in the same order. So if it has a saddle point, then there will be a Nash equilibrium for pure strategy, in pure strategies. And if there's no saddle point, I want to convince you it's guaranteed you can find a Nash equilibrium in mixed strategy. Okay. There will be a moment I'm not completely mathematical, but okay, believe me. Yeah. Okay, so this is a special case of Nash theorem, which was stated in, I just repeated, right? Finite many players, each player has finite many strategies, always have Nash equilibrium in mixed strategies. Okay, so let's prove this. So let's set things up. So we have so we have two players, player one, player two, right? So each one has two moves, okay? Move one, move two, move one, move two. And then we have a simplified payoff because this is zero-sum game. So I have A, B, C, D here. And the player two's payoff will be minus A, minus B, minus C, minus D, right? So we have, this is the setup for the small game. Now, so here the payoff are for player one, okay? Now, actually, we can be more general. So this is a 2x2 matrix with A, B, C, D. Now, you can say we have, actually, you can have different dimension, but, well, so you can consider two-player game with n strategies, right? So player one has n strategies, player two has n strategies. So you have payoff. This is a simplified payoff for player one. Okay, so the easy case is there is a saddle point. Okay, so the saddle point are defined in the same way. So the saddle point, for example, this one, will be the minimum in the row and maximum in the column. Okay, so this point, Mij is a saddle point if he is the minimum in this row, Si, and he is maximum in this column. Okay? So the theorem says if M has a saddle point, and then the saddle point is also Nash equilibrium for pure strategies. So this is an easy observation. So the reason is, okay, I'm repeating myself. I said this in a special case at the beginning of the lecture. So it says, let's look at it again, right? Does player one has incentive to move away from this point? Okay, player one will choose rows, remember? So if he moves away, because this guy is a maximum in this column, if he moves away, suppose he moved from the red one to a different column, he moved away from maximal. So he lose money. So therefore, the player one does not have incentive to move away, right? So player one does not move away from the strategy, the ice strategy, because Mij is the maximum in column J, right? So look at numbers in column J. This is the biggest number. So if you move away from the red one, you always get less. So no incentive. Now player two, how about this guy? Does he have incentive to move away from this spot? Well, no, because the Mij is a minimum in the row I. But however, this is a payoff matrix for player one. So for player two, her payoff is the negative of this, right? So if you move away, you get, for player two point of view, again, is worse, right? Because if you move away, you get a smaller number, but however, you have to take negative. So there's no incentive to move away. So if you have a saddle point, and then it is a Nash equilibrium. Okay. Although this solved the saddle point case, I want to stay in this case and make some remarks. So we'll see a little bit more about this. Okay, so let's make some remarks. So for each strategy SI of player one, so I want to explain some number is important. Okay, so for each strategy SI for player one, I want to look at the value of the minimum of numbers in this in this row, right? So the minimum, so the J will move from 1 to n, and so I'm looking at this one. I'll compare the numbers in this row. I take the minimum number. Okay? So what is the significance of this minimum number? Sorry. So this number is what she is guaranteed to win if she plays this SI. Right? Okay. Try again. So here, suppose this red guy is a minimum in this row. And then if player one play this strategy, and then this is the worst payoff. So she will get at least this many, right? Because it's a minimum. If the guy doesn't play the strategy J, she probably get more. But this is the minimum one. So guaranteed, no matter what happens, she will get at least this one. Okay? So this is the word. Okay, so I want to emphasize the word guaranteed to win. Guaranteed, right? So if you look at the minimum number, minimum entry in each row, that is the guaranteed payoff for player one. Now, suppose you take maximum of all these guaranteed values, right? That is the guaranteed return for player one, the best possible guaranteed return, right? Because if you play a strategy, the minimum among these entries will be the guaranteed return. So now you choose the guy who reached maximum. So that's the best thing you can do. Okay, you may have a chance to hit higher return, higher payoff, but there's no guarantee, right? It depends on the other guy who played this. Now this number called U sub R, R for role player, is the best possible guaranteed payoff for player one, right? Is this okay? So this number, the max min, is important because the importance is this is the best possible guaranteed payoff for player 1. Okay. Now, the actual amount won by player 1 might be larger if player 2 plays a stupid strategy, right? But there's no guarantee. So player 2 may be clever, so player 2 always play the wise, always make the wise move, right? Is it clear? So in this slide, we define some special number called U sub r, which is max min. Okay. Okay. Now, similarly, we can do this for player 2, right? So now we have to, so remember for player 2, his payoff actually is negative. So the thing has to be switched. So max become min, min become max, right? Okay, so the value of max of, okay, the negative max of this guy is what she guaranteed to win if she plays this, right? So then that brings us another important number called U sub C, C for column player, for player 2. Player 2 play columns, right? So the U sub C is min max, right? You take max first and you take min. Okay. Now this value, the negative UC, is the best possible guaranteed payoff for player 2. Right? This is just symmetric, but okay. Okay, so the same thing. The actual amount might be larger if player 1 choose a stupid strategy, right? Yes? Yes, so you are commenting on this, right? Yes. Hmm? Oh, because if you, okay, so let's look at a concrete example. Do I have a pure strategy? Oh, look at this. Okay, so look at the first row. Okay, the minimum one is -1. Well, so -1 is not very exciting, but -1 is a guaranteed return for player 1. Okay, why must be minimum? Because, okay, for example, I don't choose minimum. I choose this 2, right? So 2, if player 2 plays this guy, this strategy, then player 1 will get 2. But there's no guarantee because the player 2 can play move 2. And then in that case, player 1 will get worse, right? Now, if we look at this value, this is the minimum among the row, then no matter what player 2 does, player 1 get at least -1, right? At least -1 doesn't sound very nice, but this is what guaranteed. Guaranteed means at least, right? So you're sure you get this. So that's why you have to take the minimum. Is this all right for? Okay. Okay, now let's move to here. Okay, so we have these 2 numbers. One take max min, the other one take min max. Okay, so the general relation is the max min is less than or equal to min max. I don't know whether this is what you want to. So again, I don't know whether this is what you ask. You can swap the min max. So in any case, so we have 2 significant numbers, one for row player, one for column player. So the general fact, just from min max, we get this relation. Okay. So in order to simplify case, okay, you see this is simplified. There's still something to think of. Okay, so let's use n equal 2 to illustrate the proof. The proof in general case is similar to this. You can write it, but there are lots of I and j. So I don't want to use ij, so I want to use a simple example. So let's look at ABCD. Okay, so I want to convince you the max mean is less than or equal to mean max. Right? So this is, you choose minimum first and pick the best one. And the other way is you choose maximum and choose mean. Right? Okay, so I want to convince you if you choose the minimum of the first row and minimum second row, that's these two numbers, then you take max. So this left-hand side is less than or equal to, you choose the maximum of this column, and then you choose maximum of that column, you get two numbers, then you choose the minimum among them. Okay? So I want to convince you that left-hand side is less than or equal to right-hand side. Right? So if you never seen max mean before, this is a very strange. Okay, so let's try. So the argument goes like this. So first, look at this term, the mean of AB. So the minimum of them is less than or equal to any one of these, right? Because you always choose minimum. So the minimum of this is less than or equal to A, right? For example. Because you always choose the lower guy, so it's less than A. Now A is obviously less than max of A and C, right? Because you always choose the bigger one. So this is true, right? You agree. The same thing happened for B. So the minimum of A and B is less than or equal to B, and is less than or equal to maximum of anything with B inside is at least B, right? So we have these two inequalities. Okay, now this number, minimum of AB, is less than, okay, so on left-hand side, I have mean of AB. On right-hand side, I have max this and max that. Okay, now this number, mean AB is less than this, max this. Mean AB is less than max that. If he is less than both of them, he is less than or equal to the smallest one, right? Because no matter who you choose, it's always less than. So choose the minimum one, okay. Choose maximum one. So therefore, the minimum of AB is less than or equal to the right-hand side, this terrible expression. Okay? Now the same reason, so I choose AB, it's the same. If I choose CD, I can do the same argument. So the minimum of CD is also less than or equal to the right-hand side. So in other words, the right-hand side beat any one of these. So it beats the maximum one, because he beats both. No matter you choose max or choose min, this guy kill everybody, right? So therefore, the right-hand side is bigger than left-hand side. Okay, so that's the proof. Okay, now, after we introduce these two values, UR and UC, now if they happen to be equal, and then we will have a saddle point. So in general, it's less than or equal to, but when there is a saddle point, they are equal. Okay, so if M has a saddle point, then the two values are all equal to the value at saddle points. Okay. Okay, so again, we use n equal 2 to illustrate. Right? So let's assume this guy has a saddle point. Okay, so A star. A star could be one of these. Right? So now the saddle point is a minimum in a row. So A star is less than or equal to UR. Right? UR take the max among the minimum. So U star will beat minimum of this particular row. So A star will be less than U of R, because U sub R is the max of all the means. Right? Now also, it is a maximum of a column. So this guy is bigger than U sub C, because U sub C take the minimum of all the max, right? So the particular instance is bigger than the minimum. Okay, so we have these two. Now that's enough. Okay, so now you read it again. U sub c is less than or equal to a star. So from this, we get there. Now a star is less than or equal to u sub r. So a star is less than u sub r. But we have shown u sub r is always less than or equal to u sub c. It's a previous lemma. So therefore, we have this. But you see, in this inequality, the first term equal to the last term, so everybody has to be same, right? So therefore, we have that. Okay? So if you have a saddle point, by playing with the property of saddle points, you know that both the row player and the column player can get their values. Okay. Now, on the other hand, if you can achieve the equality, so in general it's less than or equal to. If it happens to be equal, then M must have a saddle point. Okay. So again, we look at a simple case. So there are lots of sub-cases. But let's assume the maximum of the mean achieved at first row, and the minimum of the column achieved at first column. Other cases are similar. You just randomly choose a row and a column. So I choose 1, 1. So the argument is the same. Okay. So other cases are similar. Okay, so now we use the condition u of r equal u of c. So we know that the minimum of AB is the same as maximum of AC. Okay? So then what happens? Then, okay, the maximum of AC will be bigger than or equal to A and bigger than or equal to C because it's maximum. So this guy is bigger than or equal to that. But he is also minimum, right? Because we assume they are equal. So he is also minimum of this. So minimum of AB is certainly less than or equal to A, less than or equal to B because it chooses a minimum. So you are here. Okay, so read it together. So no matter you choose A or you choose C, it's always less than or equal to B, right? So A will be less than B. Now you choose C, C will be less than A, right? So we have A less than B and C less than A. So this says A is a saddle point, right? Because A will be the minimum in first row and maximum in the first column. So we'll have a saddle point. The other cases are similar. Okay. Okay, so now, okay, so let's continue the discussion a little bit. So we have, I try to sell you this, right? I said, assuming we have a saddle point, and then so the saddle point will be Nash equilibrium, and both players must choose the strategy contain a saddle point, right? So that we can hit the Nash equilibrium. But wait, sometimes the matrix can have more than one saddle points, right? For example, this matrix have this is Mij is a saddle point, MKL is also a saddle point. Now the player can choose this. So player 1 can choose a row containing the saddle point. For example, player 1 choose row I. Right? Okay, player 2 must choose one contain a saddle point. So he may choose L. Well, if you take intersection, it didn't hit knowns. It doesn't hit this red, doesn't hit this red. So we have to look at this value, right? So if player 1 choose this, player 2 choose that, are they going to meet at a Nash equilibrium? Well, the answer is yes. So there's a tutorial problem. The tutorial problem says, tutorial problem didn't use IJ. I choose some specific number like 2, 3 or something. But the idea is exactly the same. So in the tutorial problem, we'll know that if you have this situation, all these 4 points, the 2 red and 2 question mark, are all saddle points, and the values are equal. So therefore, if you play I, he play L, they also hit a saddle point with the same value. So it doesn't change anything. Okay? So now, this is the last remark, then we'll move into the mixed strategy. Okay, so this part, I'm going to use it in a moment. So I want to say this. So in this special case, when M is 2 by 2 matrix, we have this following fact. So this guy, M, has a saddle point is equivalent. So the fancy way of say equivalent is if and only if. Okay, we learned that in week 3 or something. So it says M has a saddle point if and only if it has a dominated row or a dominated column. So this links the existence of saddle point and the existence of dominant row or dominant column. Is it clear what is a dominant row? So in this case, if A is bigger than C, B is bigger than D, and then the first row dominant the second row, right? So the dominant is quite intuitive. You see, if first row, every entry is bigger than the corresponding entry in second row, then first row dominates the second row. Okay, so should we? Okay. I was wondering whether I should prove this or. Okay, so let's quickly go through it. So for if and only if, you have two directions, right? So you go from here, from left-hand side, you have to derive right-hand side. From right-hand side, you have to derive left-hand side. Okay, so let's go from left to right. So suppose I have a saddle point here, then I must give you a dominant row or dominant column, okay? Okay, so, well, A, B, C, D, one of them is a saddle point. Let's assume A is. Okay, so I don't want to get too complicated. So let's assume A is, this position is a saddle point. So what does it tell me? So by definition of saddle point, A is the minimum of the row. So A is less than or equal to B, so that he is a minimum. Okay? A is also the maximum of first column, so A is bigger than or equal to C. Right? So we have this. A is less than or equal to B, A is bigger than or equal to C. Now look at D. Compare D with B. There are two cases. D is less than or equal to B or the other way. If D is less than or equal to B, then we have, okay, what do we have? If D is less, okay, C is less than or equal to A. If D is less than or equal to B, then the first row completely dominates the second row, right? Because C is less, D is also less. So we have a dominant row. Okay. Now, how about the other way? If D is bigger than or equal to B, right? It's not less than B, it's bigger than or equal to B. And then read this. So D bigger than B, B bigger than A bigger than C. So D is bigger than C. So D is bigger than C. But we also know B is bigger than A. So the second column will dominate the first column. So in whatever case, you always find the dominant row or dominant column. Okay. So this is from left to right. Now, how about the other way? Suppose I have a dominant row or a dominant column, can I have a saddle point? The answer is yes. So suppose the first row dominates the second, right? So suppose this guy, AB, dominant CD. So in other words, A is bigger than or equal to C, B is bigger than or equal to D, right? Now let's consider there are two cases. A is less than or equal to B. If A is less than or equal to B, good. So A is saddle point because A will be minimum in first row, but maximum in the first column, right? Because A is less than B, is minimum in row. A is bigger than or equal to C, so A is maximum in the column. So A is a saddle point. Now, the other way, if A is bigger than or equal to B, so I claim B is a saddle point. If A is bigger than or equal to B, because B is the minimum, in first row, but B bigger than D. So B is a maximum in the second column. So B will be a saddle point. So no matter what you try, there's always a saddle point. So in this small game, having saddle points the same as having a dominant row or dominant column. We are going to use this in a moment. Okay, so the catch is this lemma may not be true if you have a big matrix. Then you have to use other method. So this is very, very special. Okay, so now we move on to the mixed strategy, right? So we have seen that if the game has a saddle point, it has a Nash equilibrium, easy. Now what happens if the game does not have a saddle point? So I have to give you a Nash equilibrium for mixed strategy, okay? So now assume this guy has no saddle point. Okay. So in this case, the UR and UR and UC are not equal because we have shown if they are equal, you have a saddle point. So they are less. So there's no Nash equilibrium for pure strategies. Okay, so you have to go to the mixed strategy. Okay, so we show that M has a Nash equilibrium in mixed strategies. Okay, so we do things slowly and step by step. Okay, so now first we bring in. So this is like a revision. So we say the same thing. Instead of using 4, 1, 3, 2, we use ABCD. Okay, so we now have a payoff matrix with probability. So we introduce P1 minus P, Q1 minus Q, right? So player 1 has 2 strategies, S1, S2. Player 2 has 2 strategies, T1, T2. Then this matrix stands for the payoff for player 1, okay? And then the probability is as shown, okay? Now we repeat our procedure. So we calculate the expected payoff. Okay, so from player 1's point of view, okay, so let's repeat our argument. So from player 1's point of view, if player 2 plays T1, the expected payoff is A times P plus C times 1 minus P, right? A times P, A times probability P, plus C times 1 minus P. Okay? So if you simplify, you get, not simplify, if you combine, you get bracket A minus C times P plus C. Okay? Now, if player 2 plays the second strategy, T2, the expected payoff for player 1 is B times P plus D times 1 minus P. Okay, so is B minus D bracket times P plus D. Okay? Now, the guaranteed payoff for player 1 is the minimum of the two. Right? If player 2 plays this, he get this reward. If player 2 plays that, he get that reward. So at least he'll get one of them. So the guaranteed expected payoff will be the minimum of these two numbers, right? So it's a function of P. If P changes, then this minimum could change, right? So you are with me so far, right? So I'm saying same thing, but in terms of ABCD. Okay. Now, okay, so let me remind you where are we. So we have this matrix, and we study the minimum of the two numbers. Okay? Now, here I have to use the assumption we don't have dominant rows. Okay. So, sorry. I'm studying these numbers, so I'm going to draw the two lines as we have seen. Now, the difficult part is to say in whatever A, B, C, D, these two lines always cross. You cannot have one line above the other. Sorry. One more time. I'm going to, okay, we are studying these two numbers, okay? I don't read the expression. We are studying these two numbers. I want to convince you if I plot the two equations, they always cross. So we can always find some special spot. Okay. So what happens if they don't cross? Then one line is above the other. Then they will not cross. So I have to convince you that will not happen. If that happens, you have saddle points. Okay. Okay. So let's carry out the plan. So since we don't have dominant rows, because we have no saddle points. So remember, we assume we don't have saddle point, and just at the very end of the discussion, I convinced you saddle point is the same as dominant row or dominant column. So we don't have dominant rows. So look at the coefficient of A minus C and B minus D. If one of them is positive, the other one must be negative, because, right? So these two guys must be of opposite sign. Otherwise, suppose both of them are positive, it means A is bigger than or equal to C, A is strictly bigger than C, B is strictly bigger than D. The first row will dominate second row. But we say no dominant. So these two signs has to be different. In our example, it's the case because, right, we always have the case. Right? Where is it? So in our case, in the examples, it always one equation with a positive, one equation, the coefficient of Q is positive. The other one is negative, right? If you look at the P case, okay, one coefficient is 2, is positive. The other one must be negative, is negative, right? So this comes from there's no saddle points. Okay, so we are here. Since we don't have dominant rows, so these two are of opposite signs. So let's assume A minus C is bigger than 0, B minus D is less than 0. It doesn't matter. If you flip around, it's the same. Okay, so in other words, C is less than A and B is less than D. Okay, so you move this to the other side, you get C is less than A, B is less than D. Now, the next thing I want to, okay, so I'll show you the graph. So I want to show the graph are like this. So I have to compare C and D and B and A. Because this, for the expression A minus C P plus C, when P is 0, the value is C. When P equal 1, the value is A. I want to, so this is certainly going up because A minus C is bigger than 0, so this thing goes up. The other guy, B minus D, P plus D, is like this. When P equals 0, the value is D. When P equals 1, the value is B. Right? So if D is above C, B is less than A, then they have to cross. So I have to convince you that D is indeed above C and A is indeed above B. Okay, so that's why I do here. Okay, so if D is, sorry, right? I want to show you that C is less than D. Okay, so I want to rule out D less than C. If D less than C, then what happens? Then A is bigger than C, C is bigger than D, and D is bigger than B. So A is bigger than B. So we have A is bigger than B, C is bigger than D. So we have A is bigger than B, C is bigger than D. So we have a dominant column. That's also not possible. So therefore, C has to be less than D. Well, I guess you had enough of these inequalities. So similarly, B is less than A. So we have this situation. So D is above C, and A is above B. So one line has to go this, the other one has to go that. So they have to cross. Okay? So, so the setting is, again, we study these two lines, and the condition we have is C less than D and B less than A. So in this case, this ensures that the two lines will cross. Okay. So by the diagram, we know that this intersection P star is special. So you can solve P star, which is this. And then the value it achieves is this VR sub P is here. Okay. So the V sub R is the best guaranteed expected payoff for player one. You see in this screen, it doesn't show. Actually, I make the lower part thicker. So look at this line from C to this intersection and go down. So this is the guaranteed payoff for player one, right? Now, this special point is the highest. So this is the best expected payoff player one can ever hope. So therefore, we argue that this point is special. Okay? So if you calculate the expected value for the role player is this. It is achieved at this point. Okay? So a coordinate of this is these two guys. Okay? Now do the same for player two. Okay, so player two will, okay, I won't bother you. So you get some linear equation, and then you can, okay, so you get some payoff here, and then you get equations, and then you plot the line. But somehow you are interested in, now you have to observe this half, because player two's payoff is the negation of these. So this looks like I'm going to the minimum, but no, because of the negation, actually I have to flip the top, this part. So this point actually, if you take negation, is the highest point player two can get, right? So the rest are similar, so you get this payoff. So at the point Q star, you get the special value V sub C, V sub column player. Okay. So if you take negative value, that is the best guaranteed expected payoff for player two. The reason is similar. Okay, so the conclusion is this point is special. When P equal P star and Q equal Q star, you get a Nash equilibrium of this small game. Okay. And so I guess hopefully that convinces you the Nash equilibrium always exists, right? So let me just quickly recap. So how do we show in this case? So we first look at, look at this payoff. Do you have a saddle point? If yes, okay, I have the Nash equilibrium in pure strategies. Now, suppose you don't have saddle points, and then I do this, I assign probability and do this funny drawing. And then using the assumption it doesn't have saddle points, I can see the graph has to be like a line crossing. So I find the intersection and convince you the intersection is special, is a Nash equilibrium. So that's the overall argument. There are some details missing, but this is not required. Any proof, you know that in the end we are going to do true or false, right? So you are not going to require to write things like this. Okay, so next week we are going to talk about voting. So it's a sort of application of game theory and with some special flavor. Okay, so I'll stop here.